Okay, so this is the second half of the video for chapter 15. I'm going to do the lecture portion first, and then you're going to watch the practice. So for some reason, this sounds really familiar. I think I talked about it already, but homogeneous versus heterogeneous equilibria. Homogeneous is when it occurs in the same phase. The reactants and the products are all in the same phase of matter. And heterogeneous is when they are in a different phase. The value used for the concentration of a pure substance is always 1. So if we're looking at the decomposition of calcium carbonate, this is a heterogeneous equilibrium. This E obviously should be a arrow. Okay, notice the different phases. You have solid phase, gas phase. And therefore the Kc is going to be equal to the concentration of the CO2 gas. And the Kp would be equal to the pressure of the gas. So some rules for deducing equilibrium concentrations. 1, you have to know all the initial and equilibrium concentrations. I talked about this the other day when I spoke about the Rice table: reaction, initial, change, equilibrium. For anything for which initial and equilibrium concentrations are known, you're going to calculate the change. Remember, the initial concentration for the products is always going to be 0 because initially there are no products. And then you use the balanced equation to find the change for all other reactants and products. You can then use the initial concentrations and the changes to find equilibrium concentration for all species. So you're not going to do all of these. It's going to depend on what you're given. If you're given initial and equilibrium, you can calculate change. If you're given initial and change, then you can calculate equilibrium. Sometimes you have to use one reactant to then solve for either the change or the equilibrium, and then use that to solve for the product, and or vice versa. And then you calculate the equilibrium constant. So here's an example. A closed system initially containing 1 times 10 to the negative 3 molarity of hydrogen gas and 2 times 10 to the negative 3 molarity for iodine gas at 448 Celsius is allowed to reach equilibrium. The analysis of the equilibrium mixture shows that the HI concentration is 1.87 times 10 to the negative 3. So we know the initial concentrations of both the reactants. We know the equilibrium concentration of the product. We know what the change is going to be, right? The change is going to be minus x plus 2x, right? Based on the stoichiometry of the equation, meaning the coefficients. So they didn't write the reaction here, but you can see that I've got the initial concentrations in. My product is 0, and I know the final concentration. So a couple of things that we also know is that, and they didn't write it in here, is that, let me just put it above it. I'm going to put it here. So this represents 2x. Okay, this is plus 2x. So the 1.87 times 10 to the negative minus 3 actually represents 2x. If we were to put the change in, this would have been minus x, and this would have been minus x. So because we know what that is, right, then we can figure out what the change, we know what the change is, right? We know what the change is. So if you take 1.87 e to the negative third and you divide it by 2, you get 9.35 times 10 to the minus 4. So the 1.87 is the equilibrium concentration of the HI, but that's represented as 2x. We know the change in H2 and I2 is x. So half of that is the negative 9.35 times 10 to the negative 4. Then we can subtract that from the initial concentrations, and we get our answer of 6.5 times 10 to the minus 5 and 1.065 times 10 to the minus 3. So just remember that if you're given the equilibrium concentration and you don't know the change, that represents the change for that substance. So now I know that my expression is going to be HI squared because of the coefficient in front of the HI divided by the products. I substitute in and I get my answer. Now remember that the equilibrium constant does not have units. You should just double check, make sure that you get the same answer mathematically. Make sure you're using parentheses because your calculator does not understand the order of operations. Now, is this mixture in equilibrium? Meaning, which way did it go? Did it shift to the left? Did it shift to the right? Well, to answer these questions, we calculate what's called the reaction quotient, which I did talk to you about a little bit in the last video. Q looks like the equilibrium constant K, but the values are used to calculate it are at the current conditions, right? It's not at equilibrium. It's like right at this moment. And to calculate Q, we substitute the concentrations or the pressures of the reactants and products at any given time during a reaction into the equilibrium expression. So this is important. If Q is less than K, we know that the reaction will need to proceed to the products. If K equals Q, we're at equilibrium. And if Q is greater than K, then we're going to have to drive the reverse reaction and it will proceed toward the reactants. So if you don't have this in your notes yet, this is a good time to pause and write this down. So if you know the equilibrium constant, you can find the equilibrium concentrations from the initial concentrations and changes based on the stoichiometry. So this is going to be very similar to what I just showed you in the example. It says you'll set up a similar table to the ones used to find the equilibrium concentration, but the change in concentration is now a factor of X. And I've already demonstrated this for you, so we're just reinforcing it. So here you have a 1 liter flask filled with 1 mole of H2 gas and 2 moles of I2 gas. Given the Kc of 50.5 at 448, what is the equilibrium concentrations of H2 and I2? So you have your initial concentrations, your HI is 0. You know that the change is minus X and minus X because reactants are used up. Product is 2X because products are being formed, and the stoichiometry shows 2 moles. So we have 1 minus X, 2 minus X, and 2X at equilibrium. Nothing new here. We've done this. Now, though, we are going to solve for X. So we have 2X squared, right? Because it's 2X, but it's squared. And then we have that over 1 minus X and 2 minus X. And we get 50.5. We solve for X using the quadratic formula. You can use a quadratic formula calculator. I'm not going to make you do that by hand. I will put a link in the email to you if you don't have access to one already. Also, I would never give you a quadratic formula on an assessment, just so you know. All right, so here's another example. Oh no, this is the last part of the example. So we figured out that what our X was, and X has to be subtracted from 1 molar and 2.323 makes no physical sense. So we take 1 minus 0.935, 2 minus 0.935, and then we multiply 0.935 by 2 to get all of our equilibrium concentrations. All right, this is really where I wanted to be. Le Chatelier's principle. So if a system is at equilibrium and it's disturbed by a stress, and that stress is temperature, pressure changes, or concentration changes, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So I want you to imagine one of those long clown balloons. It's like really long and thin, and you can twist it into a shape. Well, if you're just holding the clown balloon in front of you and you squeeze the right side of the balloon, which way is the air going to go? The air is going to go toward the left. You squeezing the balloon is like applying a stress. It's like increasing temperature, right? Increasing concentration. If you take your hand off the balloon on the right side, which way is the air going to go? It's going to go back to the right. So that's like decreasing the stress. So what I'm trying to explain to you is when you increase the stress on a system, the shift is to the opposite side because you're trying to counter that stress. If you decrease the stress of the system, the shift is toward that decrease because you're trying to fix it. Now, the only one that has a special rule, notice I said temperature and concentration changes. Pressure has a special rule, and when we get to pressure, I'll talk to you about that. So, we're going to go through these different examples. Let me see if I can make this a little bigger. Okay, here we go. So concentration, adding or removing a reactant or product. If a substance is added to a system at equilibrium, the system reacts to consume some of the substance. So in this case, you have the initial concentration, right? And it makes the product. That's equilibrium. You see the back and forth arrow. But when I add substance, see when I add more blue, right? That means I have more of that for the other reactant to react with. So I'm going to make more product. So my shift is going to be toward the right. You can see I made more product and equilibrium is reestablished. Now, if I decreased, my cat walked on my computer. If I decrease the substance, then the opposite will happen. It will shift toward the decrease. I'm going to go to temperature next. If temperature of a system is increased, the system reacts as if we added a reactant to an endothermic reaction or a product to an exothermic reaction. So the equilibrium shifts in the direction that consumes the excess reagent. So if I increase temperature, it's going to shift right. If I decrease temperature, it's going to shift left. If it's exothermic and I increase temperature, it's going to shift left. And if I decrease temperature, it's going to shift right. Because remember, how does temperature appear when we write a reaction? Temperature is going to appear as a numerical value. So it could say positive 25 kilojoules, right? And that would be on the left. If it says negative 25 kilojoules, then it would be on the right. Or it could just be written into the reaction. So whenever I have an increase in concentration or an increase in temperature, it shifts to the opposite side. If I decrease it, it shifts toward the side. Pressure is different because if I increase pressure, I'm going to change the volume. So if I increase pressure, the reaction is going to shift to the side with the least number of moles of gas. because that's where it's less crowded. So that's that. Okay, so let's go through these now in each example. Here I have a change in reactant or product. So adding a reaction component will result in some of it being used up. So here you can see my initial equilibrium. I have H2 and N3. I know they're in equilibrium because the graph is flat. But now I added more H2. Look at how my green line spiked up. So if I have more H2, what's going to happen? I am going to, make more product. I'm going to make more NH3, and then you can see that equilibrium is reestablished because the flat line again. My N2, my N2 is going to decrease because when I added more H2, it now has more, it combines more with N2. So H2 initially increases, but then it's going to decrease because the H2 is colliding with the N2 to make more NH3, and equilibrium is reestablished. Change in volume or pressure. When gases are involved in an equilibrium, a change in pressure or volume will affect equilibrium. Higher volume or lower pressure favors the side of the equation with more moles of gas. So I told you if I increase the pressure, which would be lower volume, it switches to the side with less moles of gas because it's going to be less crowded. So this is just saying it in the opposite way that I originally said it. So if I have low pressure, it means I have more volume. It's going to go to the side with more moles. If I have high pressure, lower volume, it's going to go to the side with less moles. Change in temperature. Is the reaction endothermic or exothermic as written? That matters. Where's your heat? Is it on the left or the right? If it's on the left, then it's acting like a reactant. It will drive toward the products if it's increased. If it's on the right, then it's acting like a product. It'll drive toward the reactants if the heat is increased. So here you have heat on the left, and you have the cobalt ion, which is pink. And when you add that to chlorine, it forms another cobalt ion that is blue. So what happens is when I increase the heat, it shifts to the opposite side and the reaction appears blue, because it's going to favor this blue ion. When I decrease the heat, it's going to shift to the left and it's going to turn pink. And I actually do this with my Regents class. But the original solution is a combination of is lavender. So the original solution is like this lavender, like bluish lavender color. So when I increase the heat, it turns blue, forming the COCl42-. And when I decrease the heat, it turns pink, forming the COH2O6 2+ ion. An exothermic equilibrium. So the Haber process, remember that's the process that produces ammonia from nitrogen gas and hydrogen gas, is exothermic. So if it's exothermic, one would think that cooling down the reactants would result in more product. However, the activation energy for this reaction is really high. So this is one example where a system in equilibrium can be affected by a catalyst. So remember, a catalyst is something that reduces the amount of activation energy. So it reduces the amount of energy needed to get to that transition state or intermediate state. So your reactants are usually at A, your products at B, if this is a forward reaction. So the activation energy is lowered, allowing the equilibrium to be established at a lower temperature. So the catalyst lowers the activation energy by creating an alternate route. It does not affect the concentration of, or the amount of products and reactants that are involved in the reaction. All it does is lower the activation energy. Okay, so that's it for this reaction of this lecture. And now you're going to go to the practice.